Today we're talking about expected eligibility traces, and we're going to jump right into this now. But before talking about the eligibility traces themselves, we want to sort of set the stage for what we're talking about today. So the first thing we want to consider is just a recap of some of the common, TD algorithms or just reinforcement learning algorithms that we're used to. So if we start with a Monte Carlo update, that is basically one of the simplest ways in which you could implement an RL algorithm, and you've probably seen that before in other videos. What you do, or like the essence of a Monte Carlo update, is go through an entire episode, and then you use your rewards that you accumulate during the time as an estimate for the value of a particular state. So, in general, when we're looking at reinforcement learning algorithms, we want to find the value function, and the value function is the discounted accumulated reward of future states that we're going to get up until termination. And so that definition is clear, and one way to estimate that for a given state is to simply run the entire episode through and then use the rewards that you got to estimate the state. So that's what you do in general, and that's what Monte Carlo updates are used for. So normally then, when you would have a parameterized value function, you would take basically incremental updates according to, this procedure right here. So we don't need to go into all the details, but you have the one-step, the full return rather here. So you basically have the one-step return there, plus the discounted, the discount factor times your future rewards and discounted future rewards. So this is your expected value of future rewards starting from t+1 all the way to the end of the episode, big T. And this is then minus sort of the value function that you had before, and that's the error that you use. And then you use that as a metric to gauge how much you're updating your value function. And in contrast to this, we have something called TD learning, which I'm sure you're also familiar with. And this replaces basically the return that we're using here with an estimate of it. And that's a state estimate. So basically, it replaces it with the value function estimate that we currently have. So when we update, and that's the only difference really between them. So when we update our parameters, we do that based on the value function here instead, which, per definition should approximate this G, which is the expected discounted reward of future states. So that's another way of approaching it. And then these two algorithms differ in a number of ways. So first of all, this one is forward-looking, meaning that to get this G value, you need to actually compute the entire episode because at the current time, you don't have this G. The G is basically constructed from future rewards, but you don't have them yet. Whereas if you look here, the V that we're using here is the current value function estimate. So this is not something you need to sample, but it's something you already have. So this can be applied basically online and as you go, whereas this needs to happen at a later stage. So that's one difference. Another difference is that the V here is generally biased. So the TD learning approach is usually a biased approach, but the Monte Carlo one has a high variance in general because this G function, it can vary a lot between episodes depending on what the outcome is and depending on how, what your environment looks like. So potentially it's not the best estimate for that sake. And as a trade-off between these two, we have something called TD lambda. And in TD lambda, we're basically getting a way to interpolate between these two edge cases. So this is basically the edge case where you use all of the full returns going forward in the episode that you could. And this is the case where you're not using any of them. But you could imagine doing something in between, which is what this other estimate, so this lambda-based estimate of the G function does. So it takes the current reward plus a discount factor, and instead of just having either the value function or G, we basically use an interpolation between them, or we use a weighted average here that depends on the parameter lambda, and so you can go in between them. And the reason why we're bringing these up is because the forward and backwards looking algorithms and also this extension from Monte Carlo to TD0 is something that will be very much of interest for the eligibility traces that we aim to discuss. So just to recap what I said before is between forward and backwards looking algorithms is that forward view algorithms use the return dependent on future trajectories. So that's what we see in the Monte Carlo case. This is based on future trajectories. And what we have to do in that case is we need to wait until the end of an episode to construct their updates because we don't have those values yet, and therefore we need to wait. On the other hand, backward view algorithms, they rely on past experience. So the result of that, or the consequence, is that you can update their predictions online during an episode. for these backward view algorithms in general, they construct what's called an eligibility trace. So it's a function at the current point of time, so t, that basically takes into account the entire trajectory. So tau is the trajectory, and then we have time 0 up until current time t. So it takes the past transitions into account, and to make it more concrete, in TD lambda then, for example, the trace is basically this part here. So when we update the parameters, as we saw on the previous slide, that can be written on this form instead, and the trace here is basically this part. So it's the one part that's, let's say, recursive, and then another one that is the gradient of the value function. And this ties into something called the credit assignment problem, which is what we're trying to effectively solve. So if we take even, let's say, a wider view or a more abstract view of this entire thing, what we're really trying to do at the most fundamental level is to give credit to the states that are responsible for a particular outcome. So when we're constructing the value function, the reason why we're doing this is we want to find out how good a given state is. And in order to do that, we need to know basically what is the effect of being in this state. And you assign the credit for that, or assigning the credit for those given states is what's called the credit assignment problem. And the eligibility traces that we discussed in the previous slide, they enable efficient credit assignment to recent sequences of states and actions experienced by the agent. So we can see that here, that the trace basically uses information from past states using, this part of the trace. So this one is calculated right now based on the current state, but this one actually takes into account the last eligibility trace that we had, taking us back one state. So there's a clear correspondence or clear dependency on previous states, and we can therefore propagate information backward throughout the values. So let's say you get a reward, and the effect of that will be that the information from that reward will propagate backwards into the states that you observed before. One thing, though, that these traditional algorithms lack is basically assigning credit to counterfactual sequences that could also have led to the same state. So this sounds a bit cryptic, but what it basically means is, let's say you got a particular reward, you're going to basically credit or give credit to the states that you were in before, but there could potentially be other ways of getting to that reward that you didn't necessarily take now. So one instance or one example would be like taking a key and unlocking a door. You would basically give rewards for doing that, but only in the particular sequence that you did. But there are many sequences in which you could pick up a key and go to a door to unlock it. And you should really be giving credit to all of them, but the current algorithms can't really generalize in that way because that requires some sort of knowledge about the environment, and that's not built into most reinforcement learning algorithms. And that's where expected eligibility traces come in. So these try to solve that problem. They allow to update states and actions that could have preceded the current state, even if they did not do so on this occasion. So it really, looks at information about the environment and then couples that with what happened in this particular state to see what other things could also have happened. So that's the general idea behind it. Before we proceed, it's important to point out that the expected eligibility traces are not the only ways that we could tackle the credit assignment problem. We're going to talk about two other ways now as well before moving on. And the first one of these is model-based reinforcement learning. So in model-based reinforcement learning, you have a model of the environment and you use that in order to train the agent in an effective way. And if you have a model of the environment, you can figure out which states lead to a certain reward, partly or like even if those states were not visited per se. So this is a very good way of actually propagating back the information. The problem with this kind of setting or these kinds of models is that you need to construct them in the first place, right? So constructing a model that's accurate can be very hard, especially when the domains grow complex. Then constructing the model becomes, close to as hard as figuring out the policy itself or the value function itself. So yeah, it's not a simple task. So it could work for some elementary cases, like when the environment is not very complex, but in general, it's not perhaps the best approach. Another way that we could tackle it would be with something called source traces. And when you use those, you model the full potential histories in a tabular setting. This is also problematic because it relies on estimated importance sampling ratios of state distributions. And these are hard to estimate in a non-tabular setting. So again, we're running into the problem of this not being a very generalizable framework. And that's what we're trying to address, or one of the things we're trying to address with these expected eligibility traces. So moving on then to the actual algorithm and the extension from the current algorithms to what we're considering now. We're using TD lambda as a starting point. So we discussed the algorithm briefly in the beginning, and there's also plenty of videos on YouTube on TD lambda. And so we want to extend this to become ET lambda, which is, well, expected trace of lambda. And we replace the trajectory-based trace, ET, with a state-based estimate, ZS. And if you think about this, this is very similar to what we did in the beginning when we extended Monte Carlo to become TD0. So what we had in Monte Carlo was G function, which represents the discounted future rewards that we're going to get in our trajectory. And we replaced that with the value function itself, or the estimate of the value function. So think about what we're doing there. We're taking the full trajectory, so we have a trajectory-based quantity, and we're replacing that with a state-based quantity. We're doing exactly the same thing here, only that it's for another part of the algorithm. So we're taking a trajectory-based eligibility trace and replacing it with a state-based estimate, okay? And the estimate then here is the expected eligibility trace. So the expected eligibility trace is defined as the expectation here is simply the expectation of the eligibility trace given the state that we're in. And the expectation here is taken over the policy and the MDP dynamics. So you take those into account and then you take an expectation of it. It's very similar to the value function, taking it back again to the replacement in Monte Carlo to TD0. Only difference is that there we were expecting or taking the expectations of discounted future rewards. And here we're taking the expectation of the eligibility trace instead. So very similar extension. And the update rule, if we just compare the algorithms, in TD lambda, we have this kind of framework. So we're updating our parameters based on, alpha times the delta or the TD error times the eligibility trace. And we're replacing this eligibility trace that is dependent on the trajectory from 0 to t with simply a state-based estimate. So it only takes into account the current state, and we have then a new function set. Okay, so taking this, or actually forming the algorithm of ET lambda would be to use an approximation here. You can see that we have a theta as a subscript for both of these, and that's meant to then approximate the expectation up here. So pure set function is this expectation, and then we're parameterizing that expectation by some sort of function. And we want to basically learn those parameters, right? So one way is to update this toward the instantaneous trace ET. And we would do that by minimizing some loss. So that could be a way of actually constructing this algorithm. Now you're you can use multiple loss functions, right? It's not like pre-specified which one to use, and there's a number of ones that you could use, but if your loss would be a component-wise squared loss optimized with stochastic gradient descent, this would basically be the outcome. So you would get some sort of update rule for your parameters, and this is what they're using in the paper. So we're not going to go into details exactly of the derivation here, but just know that, we want to approximate these or update these parameters such that we get a better approximation of the actual estimated trajectory or estimated eligibility trace. And we're doing that with some loss function. Okay, so another thing that we can note is that in TD lambda, we can interpolate between Monte Carlo and TD0. So that's what we also talked about in the first slide. We have these two edge cases. We can actually go back all the way to the beginning where we have Monte Carlo here, TD lambda here, or TD0 here, sorry, and then TD lambda at the bottom. And what we can see here is that we have some sort of interpolation. So the first part here represented the value function that we can see here, the state-based estimate, and the other component represented the trajectory-based one. So this is basically the rewards to come. And so based on how we pick lambda here, we can put more emphasis on one or the other. And we want to now do something similar in the setting that we're currently in. So we want to have some sort of interpolation between these like ET lambda algorithm that we found and then TD lambda, that is our starting point. And we can basically construct a new algorithm for this. So it's also called like ET, but it has eta as another set of parameters. So it extends the algorithm we just talked about to interpolate between these two extremes. And then it uses a recursively defined mixture trace, YT, to do this. And the recursive usage of Z in this Y component as previous stage is analogous to bootstrapping on future state values when using a lambda return. And also with one important difference to this is that the arrow of time is opposite. So when we consider the lambda return before, when we talked about basically bootstrapping the returns as in TD lambda, we looked forward, right? So the rewards that we accumulated were future rewards. But here, we're making still a trade-off between a state-based estimate and then the full history, let's say, but we're going backwards. So the time arrow, let's say, is in the other direction. And this means that we can actually estimate it directly. So we don't need to wait for future observations, even though we're using let's say a mix between a state-based estimate and then a trajectory-based one. So this is basically the algorithm here. And compared to before, we now have a component here that mixes the past trace, YT. So now, before we denoted Z, and this is more of a generalization from that algorithm. So now we're using Y instead. All I'm saying is here, we had Z basically in the ET lambda algorithm. Instead of the Z, we now have Y. And Y is quite similar to Z. So if we set eta equals to 0, this will basically just come out as Z. And then this algorithm that is constructs will be equivalent to what we had in the previous slide. But if eta is not 1, then we will basically take this part into account as well. And this is the trace component. So you can see here that this is basically the eligibility trace that we have from TD lambda, and it's basically the same component that we put in here. So this becomes, let's say, a mix between TD lambda and ET lambda. And we can also see that, or it's also written down here. So if we put in a parameter of eta equals 1, we only get the Z back, and that gives us alpha, delta, and then Z. And that is exactly what we had in the original TD lambda algorithm. If we set eta equals to 0, this part disappears, and we only get this part here. And we have a perfect correspondence to the trace component from before in the standard TD lambda. The next thing we want to look at now is some results. So basically what they found in this paper. And the first thing we're looking at is a pretty simple environment. The environment that we can see is illustrated up here. It's a Markov decision process, and we have one state down here that is the terminal state. And the goal is basically to make it down here. We can see that any action in the bottom right corner terminates the episode. So when we get here, we're finished. And as we finish, we get a reward of +1 with a probability of 0.2. Otherwise, we get a 0 reward, and we do so for all other actions and states in this MDP. So if we look at the actual value function, so we can empirically, or we can evaluate the exact value function in this case, it looks something like this. And they did a comparison between the different algorithms that we're comparing in this study. So first of all, we can see TD0 up here, then TD lambda here, and then ET lambda at the bottom. Now, TD0 is basically, it only propagates information back one step at a time because we're only using basically the value function from the previous state. In TD lambda, we propagate the information back multiple steps, and in ET lambda, we also take into account these expected traces. And what we can see, I think the most telling example is actually the first one. So this one here is when we get the first reward. So we can see here, as we said before, that in TD0, we only propagate back one step. So we basically just assign a value to the last state here. The difference to TD lambda in this case is that TD lambda propagates all the way back. So it basically assigns credit to all the other states as well. And so we can see that this improves, let's say, the speed at which you tend to learn, at least in the beginning. However, what's quite interesting here is that for ET lambda, we see that on the instance of the first reward, we're not only rewarding the trajectory that we followed, but we also reward other trajectories here. And what actually happened in this case is you got to the bottom a few times before you got the first reward. And so the ET lambda algorithm actually uses the information about this to reward those states. So it keeps track kind of where you can move and how your states interact, and then assigns credit to all of them. So we can see here on the first state already, or the first reward, that ET lambda has propagated information a lot more than the other two algorithms. And then, progressing here, we can see the same story. So basically the ET lambda converges first. We can see already here that we're very similar to the true value function up here, whereas for these ones, we don't see the same story. One thing that's quite interesting to note here is that we tend to converge well earlier with the TD0 algorithm than the TD lambda algorithm in this case, even though TD lambda is much faster in the beginning. And that's because the TD lambda algorithm is basically high variance. So we're learning quite fast, but if there's a high variance, that's going to make it difficult to converge. Whereas with TD0, it's much more steady. So we can see that learning takes a long time to take off, but in the end, we get there in a quite steady manner. ET lambda seems to combine both of these benefits into something that's both fast, but then also accurate in terms of having a low variance. So these results look very promising. The second investigation that they made is for the problem that we can see in the right corner here. So basically, you're starting in this state here, and then you can pick from one out of m different chains that transition along the path here. In the end, like in this state here, you always come back to basically a bottleneck stage before terminating. And when you terminate, or each reward in this chain is basically +1, except from the termination stage, where it's either +1 with a probability of 0.9, and then you would terminate, or it's -1 with a probability of 0.1. So you could, in most cases, you always get positive rewards for everything until you terminate, but every once in a while you get a negative reward from the final stage. And what they did is they evaluated basically how the different algorithms perform here. So what we can see first is the performance of these algorithms, or the RMSE for both TT lambda and ET lambda on the value function based on the number of branches that you're using. So what you can see is in the beginning, they're both pretty accurate, but the difference between these grows quite rapidly as the number of branches increase, especially when we get to like 32 branches, we see a noticeable difference between them. And the reason why is just because the TD lambda is not able to generalize across these different chains. So ET lambda, once it gets a negative reward, it's able to see that, okay, for all of these chains, we could have basically ended up in the same state. And so we should penalize all of them. However, for TD lambda, you're only penalizing the trajectory that you came from, and therefore you would only penalize basically one of these, even though they're always, like all of them are pretty much equivalent. We're doing the same thing and then ending up in this state. So the negative reward could really have come from any of these, but we're unable to get that information in TD lambda, and that's why we see it basically perform very poorly in comparison to ET lambda on a large number of these branches. What we can see here is also a comparison of the decay parameter lambda as for varying numbers of branches, so 8, 32, and 128. And overall, like the conclusion that they're able to draw here is that the dependence on lambda varies with the number of branches, and there's nothing concrete that we can say about exactly what these curves are going to look like. But in general, what they're finding is that the ET lambda, regardless of the number of branches, always performs better. So definitely in this kind of setting, it's beneficial to be able to generalize the penalization across these chains. And that's what we're effectively able to do with ET lambda. Continuing on the same example, so basically the example we saw in this slide, they did another study. This is basically when they're using, or what they're trying to investigate is the performance as a function of the branches, as a function of the decay parameter lambda, and also as a function of the trace parameter, as I call it, the eta here. For all of these, n is 16, which is basically the length of these chains here. And what they're doing is they're using linear value function approximation. So they're decoding the value function or encoding the value function here basically as a linear function. And the state vector then x contains a binary indicator of the branch, binary indicator of the progress along the chain, a bias that always equals 1. Again, I suppose this is some sort of remnant from something else they were investigating. And then 2 binary features indicating when it's in the start or bottleneck state. So basically this one or this one. So that's what they're using. And then a linear function of this state vector here. And then for ET lambda, they also need to use a linear expected trace, or they need to use some sort of function for the expected trace, and they're using a linear one here. And for the results, which we can see down here, they used the best constant step size alpha and lambda. So they evaluated a number of different alternatives and picked the best ones. And then they're plotting the average RMSE after 1024 episodes and then average over 10 seats. And that's what we can see in the shaded regions here. And the conclusion is that ET lambda always attained lower RMSE than TD. ET lambda always attained lower RMSE than TD lambda. And the full expected trace, 8 equals 0 here, performed quite well. So we can see basically in the 16 number of branches, here for a lambda parameter of 0.9, they did a like the interpolation between the various algorithms that we have. So basically varying eta from 0 to 1. And we can see that in this case, it performs quite well with eta equals 0. They're mentioning in the paper that this is not necessarily, this can vary quite substantially between environments. So it's not as to say that a parameter value of 0 here is always better, but probably in other environments, it would make sense to have an eta that's further up on this scale. But in general, the conclusion is still the same, that the ET algorithm outperforms the TD algorithm, and it does so across the number of branches. So that's a consistent result here. They also investigated how well this generalizes to neural networks. So they're leaving the linear value function approximation behind, and here they're actually using neural networks to investigate the results. And they're doing this for 2 Atari games. So this is Pong and Pac-Man. And similar to what we could see before, the results are basically better for this new algorithm that they developed. This is Q-learning, so now they're comparing Q-lambda and QAT lambda, and the lambda value is 0.95. And the expected traces improved learning rate compared to the baseline, which uses accumulating traces. And the expected traces extend to nonlinear function approximation. That's basically what we can say from here. So to give some background on what this result actually represents, it's to justify that we can also use this in a neural network setting. This is not obvious because in the setting that this was developed, it was basically developed for linear function approximation as a whole. And there are some theorems in the paper that relate to these linear function approximators. And because the neural networks are very nonlinear, it could be the case that these results would not generalize well at all to that setting. But what they're finding here is basically that the learning curves are better for the expected traces than for just using traces in the standard way. And we can see that through basically all of these, right? So we can see the final score is generally higher for the expected trace algorithms, and the learning curves are both faster and then also have a larger area under them. So we want to maximize the area here, right? Because if the area is large, that basically means we've got a high performance across learning. So yeah, for all the metrics evaluated on these games, the expected trace algorithm performs better than the standard eligibility trace algorithm. The final thing we want to go over before basically wrapping this presentation up is an extension to model-based reinforcement learning. So the expected traces construct a formal model of the environment, similar to what you might have in model-based reinforcement learning, because per definition, we're looking at the other states that we could have visited in order to get to a certain state. So in some sense, we're getting a model of the environment. It's important to point out, though, that this sort of model differs in several key regards from the standard state-of-the-art models that are being used normally in model-based reinforcement learning. So they point out basically 3 distinctions between these. And the first one is that the expected traces that we're now using to estimate past, or the expected traces that we're now constructing, they estimate past quantities rather than future quantities. So in the model-based setting, you normally construct a model to be able to predict the future, right? What we're doing here is we're having some model, but it's really about the past that we used in order to get to the present state. In addition to this, they estimate the accumulation of gradients over a multi-step trajectory rather than full transition dynamics. So if you have a model, as in model-based reinforcement learning, normally you would use that model to actually model the entire environment, right? So you start from an environment, you make a model that sort of accurately predicts that environment, and then you use that in combination with some algorithms to train your agent. It's kind of different here. So you're not modeling everything, you're just modeling the accumulation of gradients because that's all that is needed to basically take the step that we're interested in taking. And also they allow credit assignment across these potential past trajectories within a single update or with a single update. This is also in contrast to the model-based ones, because with the iterative, like with the model-based ones, there's usually iterative computation required to get the same effect, because the models that are being used are normally one-step prediction models, because that's the most natural way of formalizing a model if you're doing it from the point of view of a designer as opposed to something that's automatically learned by the algorithm. So those are some key differences, and these differences may be very important if you want to basically take the model-based reinforcement learning theory to the next level and to advance that level of, or to advance the theory surrounding those models. So yeah, those are quite interesting differences. And to basically conclude then what we have proposed a mechanism for efficient credit assignment using the expectation of an eligibility trace that sometimes greatly speeds up credit assignment. So for problems that are well suited for this, especially when you have various ways of getting to a particular reward, then it could be very useful and it could increase the learning rate a lot by using these kinds of eligibility traces. And they have several interpretations in addition. So one would be to counterfactually update multiple possible trajectories leading up to the current state. So that is sort of what the narrative that we've been pushing throughout this presentation quite a lot, right? So you could get to a state, but you don't necessarily take the same route. You could take different ones, and the expected traces have the effect of updating all of them. In addition, you can look at this as a bias variance trade-off, and that would be between the standard traces that tend to have a low bias and high variance, and then the estimated traces that could potentially have a higher bias, but a lower variance. So the standard traces are the ones where you actually, as we would have in the TD lambda algorithm, where you look back at a certain trajectory, and the estimated traces are the new value functions that we're putting in. And the final ET algorithm that we got basically was able to interpolate between these two. The expected traces can also be interpreted as predecessor states or features. So this would be analogous to successor states or features, but then time reversed. So as we talked about previously, the time axis with these kinds of states is reversed, right? So we're not looking into the future, but we're really using the past to estimate them. Apart from that, it's pretty much analogous. Finally, a linear algorithm preconditions the standard TD update, thereby potentially speeding up learning. So those are different ways of viewing what we're doing here, basically. And all of them have their own insights and their own sort of things that you can figure out by pursuing that sort of path of viewing the problem. So the interpretation suggests that a variety of complementary ways to potentially extend these concepts and algorithms are here. And for future research, investigating all of these different paths would be very interesting and would likely lead to basically new advances within the field. So I think that's very interesting, and I really hope to see more of this in the future. If you do so as well, please comment about it in the description, what you think of the field, where you think it's heading, and just general remarks of the video. Thanks a lot for watching, and see you in the next one.